In this lesson, we're going to look at some 3D processes and techniques using vectors, specifically processes involving projections and scalar dot products. So that means that most of what we do is going to come back to, if it's a scalar dot product question, A dot B is equal to A1 B1 plus A2 B2 plus A3 B3 in 3 dimensions, or the dot product will be equal to the product of the magnitudes because of the angle between. And if we're looking at projections, if it's a vector resolute, it will be A on B is equal to, so product of A and B over the dot product of B and itself in the direction of B. So that's a vector resolute. It gives a vector outcome. Or if we're looking at a scalar resolute, we're looking for a scalar outcome or a magnitude, then it will be the same rule, A dot B on B dot B multiplied by the magnitude of B. So that same ratio is applied, and we've either got a vector outcome or a magnitude outcome. So that makes this first question nice and easy. We've got A dot B. Now for this one, I'll write out the storage vectors. For A, our storage vector is 1, -2, 3, and -2, 3, 4. And we're looking at the product of each of these like components. So 1 by -2 is -2, -2 by 3 is -6, and 3 by 4 is 12. So we end up with -8 plus 12. We've got an outcome of 4. So scalar dot product of A and B is 4. With A dot A, we should be able to note that the angle between a vector and itself is 0. So the easiest way to approach this is looking at the product of the magnitude squared. So hopefully you recall that approach from earlier. And that means we're just looking at the square of the square root, which cancels. And we end up with 2 squared plus 3 squared plus 4 squared. So 29. We end up with 1 squared plus 2 squared plus 3 squared, and we've got a dot product of 14. Okay, so we'll step forward, and we've got a very small extension, solve an equation using a scalar dot product. So in this case, if we look at our storage vectors, we've got 1, 1, -1, dot, 3, -x2 is equal to 4. So if we apply our scalar dot product here, we've got 3 take x take 2 is equal to 4. That gives us 1 take x is 4. Negative x will be 3 when we subtract 1 from either side, and therefore x is -3. So a nice easy solution again. If we step forward to the next one, now we're looking for a magnitude of the angle ABC. So if we draw the angle ABC, that means we're going from point A to B to C. This angle that we're looking at is here. So what we will need is the vector BA and the vector BC to be able to do this. So we're going to use that rule, A dot B is equal to magnitude of A, magnitude of B, because of the angle between. So BA, using displacement vectors, will be OA, subtract OB. And that means we're looking at the vector A take B. So we've got 1, 3, -1, subtract 2, 1, 0. And we've got -1, 2, -1. That means BC will be OC take OB, or C take B. We've got 1, -2, -2, subtract 2, 1, 0. We've got -1, -3, -2. Now we just need to put that all together. We know that the dot product of BA and BC will give us the product of the magnitudes of BA and BC because of the angle between them. So the cosine of the angle between will be the ratio of the dot product over the product of the magnitudes. So I'll have 1 take 6 plus 2 is the dot product. Square root of 1 squared plus 2 squared plus 1 squared, so square root of 6. And square root of 1 squared plus 3 squared plus 2 squared. So that's 1 plus 9 plus 4, it's 14. Just have to use our calculator. And our angle will be arc cos of -3 on square root of 6 by 14. So our angle will be approximately, and you can see here after using the graphics calculator, we've got an angle which is approximately 109.1 degrees. All right. So a little bit more to that one, a bit of understanding, realizing that you need to determine those displacement vectors. But once we've got that, the calculations are pretty straightforward. So now we're going to jump into some projection examples. We're looking for the vector resolute. So that means we need a vector answer of A in the direction of B. So that means we're using the rule A on B is A dot B over B dot B in the direction of B. So A dot B will be 1 times 1, 3 times -1, -1 times 2, and B dot B will be 1 squared plus 1 squared plus 2 squared in the direction of I take J plus 2K. So we have -4 over 6, I take J plus 2K, and that'll simplify down to -2/3 I take J plus 2K. Now it's absolutely fine to leave it in that form. We could expand it out if you like, but it doesn't really matter in this scenario. Okay, so next example, we're looking at finding the scalar resolute. Scalar resolute means that we'll be using the magnitude. So for the first one, we're looking at the magnitude of A on B, which means we're looking at A dot B on B dot B multiplied by the magnitude of B. So we have 2 times -1 is -2, 2 times 0 is 0, and -1 times 3 is -3 over B dot B, which will be 1 squared plus 0 squared plus 3 squared, and our magnitude will be square root of 1 squared plus 0 squared plus 3 squared. So we end up here with -5 on 10 square root of 10, and that simplifies down to negative square root of 10 on 2. When we look in the other direction and we're saying that it's B on A, then that means we're going to say that it's B dot A, which is the same as A dot B, over A dot A, and the magnitude of A. So it will be, again, -2 plus 0 take 3. A dot A will give us 2 squared plus 2 squared plus 1 squared, and the magnitude will be square root of 2 squared plus 2 squared plus 1 squared. So we've got -5 over 9 square root of 9, and that means we've got -5 times 3 over 9, and that leaves us with -5/3. Okay, so scalar resolute, nice and easy, making sure you're being careful to see if we're looking to determine a magnitude or length, or if we're looking to find a vector. Okay, so our last example is we're looking at resolving, we'll call this one A, into rectangular components, one of which is parallel to B. So this is just a tricky way of getting us to do a projection. We've got A and B, and we want the rectangular components. One of them, which is in direction of B, so that's our U here. And then right angle rectangular, we want another here. So we want to break A into rectangular components using B as a frame of reference. Now U should be nice and easy. It will simply be A on B. We've got that projection of A in the direction of B. And then if we want to find that W, that perpendicular component, then starts here, finishes there. To do that, we'll go backwards along U, negative U, and then plus A. So along here, back up there, that gets us to that same displacement that we want for W. So A on B will give us A dot B over B dot B in the direction of B. So we will have 1 times 2, which is 2, 3 times negative 2, which is negative 6, and negative 1 by negative 1, which is plus 1, over 2 squared plus 2 squared plus 1 squared. And in the direction 2i, take 2, j, take k. So we have negative 3 over 9, 2i, take 2j, take k. And so that leaves us with negative 2/3 I plus 2/3 j and plus 1/3 k. I'm going to expand that out. In this case, it's probably better to expand it out. Now for W, we've got negative u, so negative 2/3, positive 2/3, and positive 1/3. And we're adding on A, and A is 1, 3, negative 1. Negative 2/3 gives us positive 2/3. So 2/3 plus 1 is 5/3. We got negative 2/3 plus 3. So that's 9/3. Take away 2/3, which gives us 7/3. Then finally we've got negative 1/3, subtract 1, which is negative 4/3. So we end up with W is 5/3 I plus 7/3 J, take 4/3 K. Okay, so that's our final example. I'm hoping that you can see that these skills and techniques, when applied into 3 dimensions, are very, very similar to 2 dimensions. The only scary thing is you'll have a couple of extra calculations to do. So the questions that you'll be doing will be similar to these, and you'll be applying projections and scalar dot products into scenarios with 3 dimensions.